Welcome to the Timeless Science. This is a long-form science documentary focused on deep scientific explanation. Time appears to move. It advances. It carries events from future to present to past. This sensation is universal and persistent. It governs human experience, biological aging, geological change, and cosmic evolution. Yet this apparent flow confronts a profound problem. The fundamental equations that describe physical reality do not require time to move at all. In classical mechanics, the equations of motion formulated by Isaac Newton in 1687 are invariant under time reversal. If the variable t is replaced by t, the equations remain valid. A planet orbiting a star, a pendulum swinging, or a collision between rigid bodies can be described equally well forward or backward in time. The mathematics makes no distinction. This symmetry persists in electromagnetism. James Clerk Maxwell's equations, finalized in 1865, remain unchanged under time reversal provided electric currents and magnetic fields are transformed appropriately. Light waves propagate identically whether one imagines them traveling forward or backward in time. Quantum mechanics, developed between 1900 and 1930 by Max Planck, Werner Heisenberg, Erwin Schrödinger, and others, preserves this symmetry at the level of its fundamental equations. Schrödinger's wave equation is time reversible. If a quantum state evolves forward in time according to the equation, a mathematically valid reverse evolution also exists. Even in relativistic physics, Albert Einstein's theories of special relativity in 1905 and general relativity in 1915 do not impose a preferred temporal direction. Space and time are unified into spacetime. Events are ordered relative to observers, not driven by a universal clock flowing forward. At the most fundamental level known to physics, time has no built-in arrow. This creates the central paradox. If the laws governing matter, energy, and information do not distinguish past from future, why does every macroscopic process appear irreversible? Why does a broken glass not reassemble? Why do stars exhaust nuclear fuel rather than spontaneously reigniting? Why do memories exist only of the past and not the future? The illusion of flow is not trivial. It is consistent. It is cumulative. And it is measurable. Human perception is often blamed. Psychological time is described as a construct of neural processing, shaped by attention, memory, and expectation. This explanation is insufficient. The arrow of time manifests in systems without brains, without observers, and without consciousness. Radioactive decay proceeds in one direction. Heat flows from hot to cold. Black holes absorb matter and increase entropy. None of these processes depend on subjective awareness. The question, therefore, is not why time feels like it moves. The question is why physical processes generate a consistent ordering of events that aligns with this feeling. To approach this problem, one must separate three concepts that are often conflated: time as a coordinate, time as a parameter in equations, and time as an experience direction. In physics, time is a coordinate. It labels events. In spacetime, an event is defined by its position in space and its position in time. The coordinate does not flow. It exists as part of a four-dimensional structure. This interpretation follows directly from Einstein's formulation of spacetime, where all events, past, present, and future, are equally part of the geometric description. In equations, time is a parameter. It orders changes. It allows one to describe how a system evolves from one state to another. The equations themselves do not impose preference. They allow evolution in both temporal directions. The experience direction arises elsewhere. The illusion of flow emerges from the behavior of complex systems. It is not written into the equations. It is generated by constraints imposed on physical processes. One such constraint is stability. Macroscopic systems tend to evolve towards states that are robust against small perturbations. A glass that has shattered into many fragments occupies a configuration that is statistically far more common than the precise arrangement required to form an intact glass. The equations allow reversal. The probabilities do not favor it. Probability enters physics not through ignorance, but through counting. The number of microscopic configurations corresponding to a macroscopic state can be quantified. This concept was formalized in the late 19th century by Ludwig Boltzmann. He connected macroscopic irreversibility to microscopic reversibility through statistical mechanics. But before entropy is introduced, the illusion of flow must be understood at a more basic level. Consider a simple mechanical system governed by time-reversible laws. If its initial conditions are specified with infinite precision, the system can be evolved backward exactly. In reality, no physical system possesses infinite precision. All real systems contain fluctuations, noise, and incomplete information. This is not a limitation of measurement alone. It is a limitation imposed by physics itself. Quantum mechanics enforces uncertainty. Thermal systems contain unavoidable energy distributions. Cosmological systems originate from boundary conditions that are not symmetric. As a result, backward evolution becomes unstable. Small uncertainties grow. Forward evolution remains predictable within bounds. This asymmetry in predictability contributes to the perception of temporal direction. However, predictability alone does not create an arrow. A system could be unpredictable in both directions. The decisive feature is the accumulation of records. A record is a physical imprint of an event. Fossils are records. Photographic film contains records. Neural synapses encode records. Geological strata preserve records. Records require physical substrates. They require energy. And they require irreversibility. The present is distinguished from the past because the present contains records of earlier states. The future does not. This asymmetry is physical, not psychological. In 1948, Claude Shannon formalized information theory, defining information in terms of entropy and uncertainty. Shannon's entropy quantifies the number of possible messages consistent with a signal. While originally abstract, this framework would later be shown to have direct physical consequences. The illusion of flow arises when information accumulates. Each interaction that leaves a trace increases the number of correlations between systems. These correlations are directional. They point toward earlier states. A camera records light reflected from a scene. The scene does not record the camera. A memory encodes a past experience. The experience does not encode the memory. This directionality is ubiquitous. Yet nothing in Newton's laws, Maxwell's equations, or Schrödinger's equation demands it. This leads to a critical conclusion. The arrow of time is not a fundamental property of time itself. It is an emergent property of physical processes that generate stable records. At this stage, the paradox remains unresolved. Why do records accumulate at all? Why does entropy increase rather than decrease? Why did the universe begin in a state that allowed this asymmetry to develop? The illusion of flow is not denied by physics. It is explained by it, but not yet. To proceed, the documentary must move beyond perception and into thermodynamics. The next chapter examines the principle that introduces direction where none exists in the equations, entropy. The laws of motion do not care which way time points. Thermodynamics does. The concept that introduces direction into an otherwise symmetric universe is entropy. It is not an abstract idea. It is a measurable physical quantity. It governs heat flow, chemical reactions, biological metabolism, and the fate of stars. It is the first law of nature that explicitly distinguishes past from future. Entropy entered physics in the 19th century through the study of heat engines. In 1824, Nicholas Leonard studied Carnot analyzed the efficiency of steam engines and identified limits that no mechanical ingenuity could overcome. His work was refined by Rudolf Clausius in the 1850s, who formalized the second law of thermodynamics. Clausius introduced entropy as a state function and stated the law succinctly in 1865. The entropy of the universe tends to a maximum. This statement is not probabilistic. It is directional. It asserts that natural processes proceed towards states of higher entropy and not the reverse. To understand why this matters, entropy must be defined precisely. In thermodynamics, entropy quantifies the number of microscopic configurations consistent with a macroscopic state. A macroscopic description ignores individual particle positions and velocities. It specifies bulk properties, temperature, pressure, volume, energy. Many microscopic arrangements correspond to the same macroscopic description. Entropy measures how many. Ludwig Boltzmann provided the statistical foundation in the 1870s. He connected entropy S to the number of microstates W through the relation S equals K log W, where K is Boltzmann's constant. This equation is engraved on Boltzmann's tombstone. It defines entropy not as disorder, but as multiplicity. High-entropy states are those that can be realized in many microscopic ways. Low-entropy states are rare and constrained. Consider a gas confined to half of a container. When the partition is removed, the gas spreads to fill the entire volume. The equations of motion allow the reverse process. Nothing forbids the gas molecules from spontaneously returning to one side. Yet this never occurs in practice. The reason is not dynamical impossibility. It is statistical impossibility. The number of microstates corresponding to the spread-out gas is astronomically larger than the number corresponding to the confined state. Entropy increase is therefore not about force. It is about counting. This statistical asymmetry introduces the arrow of time. When entropy increases, the system moves from less probable macrostates to more probable ones. The reverse transition is not forbidden. It is overwhelmingly unlikely. This distinction is critical. The second law does not contradict time-reversible dynamics. It supplements them. It explains why reversible laws produce irreversible behavior at scale. Entropy increase is observed universally. Heat flows from hot to cold bodies. Chemical reactions proceed toward equilibrium. Mechanical energy dissipates into thermal motion through friction. These processes are not symmetric under time reversal at the macroscopic level. The key feature is coarse graining. Macroscopic descriptions ignore microscopic detail. When a system evolves, microscopic correlations spread and become inaccessible to coarse observation. This loss of accessible information manifests as entropy increase. In classical systems, this spreading occurs through chaotic dynamics. Even deterministic systems exhibit exponential sensitivity to initial conditions. Small uncertainties amplify. Phase space volumes stretch and fold. While the total phase space volume is conserved, as proven by Liouville's theorem, its structure becomes increasingly fine-grained. Coarse descriptions cannot track it. Entropy increases relative to what can be measured. In quantum systems, entropy increase arises through entanglement. When a system interacts with its environment, their quantum states become correlated. The combined system evolves unitarily and reversibly. But the subsystem alone exhibits decoherence. Its reduced description becomes mixed. Entropy increases locally, even though the global evolution remains symmetric. This distinction between global reversibility and local irreversibility is essential. Thermodynamic entropy increase does not require fundamental time asymmetry. It requires incomplete access. However, this explanation raises a deeper problem. If entropy increase is statistical, why did the universe begin in a low-entropy state at all? Why was the early universe not already in equilibrium? Before addressing that question, the role of entropy in defining temporal direction must be clarified further. Entropy defines the direction in which processes occur spontaneously. It does not define a flow of time. Instead, it orders events. Given two macroscopic states connected by a natural process, the state with lower entropy is identified as earlier. The state with higher entropy is identified as later. This ordering is independent of clocks. It applies to isolated systems and to the universe as a whole. The second law also introduces irreversibility in practical computation. When mechanical work is converted into heat, the energy is not destroyed. It is redistributed among microscopic degrees of freedom. Recovering it would require coordinated motion of an astronomical number of particles. This coordination does not arise spontaneously. The same principle governs biological processes. Metabolism consumes low-entropy energy sources and produces high-entropy waste. Living systems maintain local order by exporting entropy to their environment. This does not violate the second law. It exemplifies it. Importantly, entropy increase is not synonymous with disorder. Crystallization can increase entropy. Structure formation can accompany entropy growth when energy is released and dispersed. What matters is not visual order, but phase space volume. The arrow of time emerges wherever entropy production occurs. This includes gravitational systems. In the early universe, matter was distributed nearly uniformly. Under gravity, this uniform state corresponds to low entropy. As matter clumps into stars, galaxies, and black holes, gravitational entropy increases. Black holes, as shown by Jacob Bekenstein in 1973 and Stephen Hawking in 1974, possess entropy proportional to the area of their event horizons. They represent some of the highest entropy objects known. Thus, entropy governs cosmic evolution as well as laboratory processes. Yet entropy alone does not explain memory. It explains irreversibility. It explains direction. But memory requires something more specific, the creation of durable correlations that persist over time. Entropy increase is necessary for memory formation, but not sufficient to explain its asymmetry. The second law explains why processes leave traces rather than erase them. It does not explain why the universe began in a condition that allowed such traces to accumulate. This limitation is not a failure of thermodynamics. It is a boundary condition problem. By the mid-20th century, physicists recognized that the arrow of time could not be derived solely from local laws. It depended on global conditions. The universe had to start far from equilibrium. Without that initial asymmetry, entropy would not have room to increase. No arrow would emerge. Entropy does not flow. It accumulates. And with it, the world acquires direction. The second law explains why processes are one way. It does not explain why the universe was prepared in a state that made this possible. That question lies beyond thermodynamics alone. The next chapter confronts this directly. It examines the initial conditions of the universe and the extraordinary fact that the cosmos began in a state of remarkably low entropy. Entropy explains direction. It does not explain origin. The second law of thermodynamics states that entropy tends to increase. This statement presupposes something crucial, that there exists a direction in which entropy can increase. That direction is not defined by the law itself. It is defined by initial conditions. Every entropy gradient points away from a boundary. In laboratory systems, that boundary is imposed by preparation. In cosmology, the boundary is the beginning of the universe. This creates a deeper paradox than any encountered so far. The universe did not begin in equilibrium. It began in an extraordinarily low entropy state. Without this fact, no arrow of time would exist. No irreversible processes would dominate. No memory, no structure, no evolution. This is not a philosophical claim. It is a quantitative one. Observations of the early universe, particularly the cosmic microwave background radiation measured by the COBE satellite in 1992, WMAP in 2003, and Planck in 2013, reveal a universe that was remarkably uniform. Temperature fluctuations were on the order of 1 part in 100,000. Matter and radiation were distributed with extreme smoothness. Uniformity may appear disordered. In thermodynamics, it is not. For systems dominated by gravity, uniformity corresponds to low entropy. This distinction is essential. In non-gravitational systems, equilibrium corresponds to uniform distributions. In gravitational systems, equilibrium corresponds to clumping. Gravity reverses intuition. A gas in a box reaches equilibrium when it spreads uniformly. A gravitating system reaches equilibrium when matter collapses into compact objects. Stars, galaxies, and black holes represent higher entropy states than diffuse matter. In the early universe, matter was spread almost perfectly evenly. Gravitational degrees of freedom were unexcited. There were no black holes, no stars, no galaxies. From a gravitational perspective, entropy was extremely low. Roger Penrose quantified this in the late 20th century. He estimated the entropy of the early universe and compared it to the maximum possible entropy allowed by gravity. The difference was vast. The probability of the universe beginning in such a low-entropy configuration by random selection was estimated to be on the order of 1 part in 10 to the power of 10 to the power of 123. This number exceeds astronomical scales. It exceeds combinatorial intuition. The low-entropy beginning is not a small deviation. It is an extreme boundary condition. This fact cannot be derived from the known laws of physics. General relativity allows many possible initial states. Quantum field theory does not select one. Thermodynamics does not constrain the beginning. The arrow of time therefore depends on something not encoded in local dynamics. The universe was prepared. This preparation does not imply intention. It implies constraint. The initial state occupied an exceptionally small region of the available phase space. To understand why this matters, consider entropy evolution. Entropy increase is a process of exploration. A system moves from a constrained region of phase space to a vastly larger one. The arrow of time points away from the constraint. In cosmology, the constraint lies at the Big Bang. The Big Bang itself is not an explosion in space. It is an expansion of space. This expansion does not by itself generate low entropy. Expansion can occur from equilibrium states as well. What matters is the structure of the fields and geometry at early times. In classical general relativity, spacetime curvature encodes gravitational degrees of freedom. Penrose introduced the Weyl curvature hypothesis to formalize this insight. The Weyl tensor measures tidal distortions and gravitational radiation. In the early universe, the Weyl curvature appears to have been near zero. Gravitational degrees of freedom were suppressed. This corresponds to low gravitational entropy. As the universe evolved, small density fluctuations grew under gravity. Structures formed. Black holes emerged. Gravitational entropy increased dramatically. The arrow of time therefore aligns with the growth of gravitational structure. This perspective resolves an apparent contradiction. The universe becomes more structured over time, not less. Yet entropy increases. Structure formation is not a violation of the second law. It is its gravitational expression. Still, the origin of the initial smoothness remains unexplained. Inflationary cosmology, proposed by Guth in 1981 and refined by Linde and others, addresses part of this problem. Inflation explains why the universe appears flat, homogeneous, and isotropic. It explains the origin of small perturbations. It does not explain why the inflationary state itself was low entropy. Inflation requires a special initial condition to begin. It does not eliminate the need for one. Quantum cosmology has attempted to address this. Proposals such as the Hartle-Hawking no-boundary condition and the Vilenkin tunneling proposal offer mathematical frameworks for describing the universe's origin. These models remain speculative and unverified. None provide an empirically confirmed mechanism that selects a low-entropy beginning uniquely. What is known is this: without a low-entropy initial state, entropy would already be maximized. No macroscopic error would exist. All processes would fluctuate symmetrically. Memory would be impossible. The universe's initial condition is therefore the ultimate source of temporal direction. This has a profound implication. The arrow of time is global. It is not generated locally. Local irreversible processes inherit their direction from cosmological boundary conditions. This explains why the arrow points the same way everywhere. Chemical reactions, biological evolution, geological processes, and human cognition all align. They share a common past. If entropy increase were purely local, different regions could exhibit opposite arrows. This is not observed. The arrow is universal. This universality reflects the uniform low-entropy beginning. The Big Bang is not merely a temporal origin. It is an informational origin. It defines the initial constraints from which all records emerge. Every memory, every fossil, every photon carries information that ultimately traces back to that initial condition. The past is special because the universe began in a state that allowed it to be recorded. At this point, the paradox sharpens. Why should a low-entropy boundary condition produce memory? Why does entropy increase manifest specifically as stored information about earlier states? Entropy alone explains irreversibility. It does not yet explain remembrance. To answer that, the analysis must move from cosmology to physical substrates. Memory must be treated not as a psychological phenomenon, but as a physical process governed by thermodynamics and information theory. The next chapter addresses this directly. It examines memory as a material operation and shows why remembering is inseparable from entropy production. Memory is not an emotion. It is not introspection. It is not narrative. Memory is a physical process. This statement is not metaphorical. It is literal. Every instance of memory corresponds to a physical change in matter. No exception has ever been observed. When a system remembers, something in the universe is altered in a durable way. That alteration obeys the laws of thermodynamics. The confusion arises because human memory is experienced subjectively. Thoughts, recollections, and identities appear internal. Physics does not recognize internal states unless they are instantiated in physical degrees of freedom. Neurons, synapses, molecular conformations, and electromagnetic states are the carriers. Without them, memory does not exist. This is not a limitation of neuroscience. It is a universal constraint. A photograph is memory. A fossil is memory. A magnetic domain on a hard drive is memory. A scar in a crystal lattice is memory. All of these are records. All require energy. All require entropy production. To understand why memory is directional, one must abandon psychological language entirely and analyze memory as record formation. A record is a stable correlation between two systems. One system undergoes a change. Another system changes in a way that encodes information about the first. The correlation persists. That persistence defines memory. In 1927, the physicist Leo Szilard demonstrated that information has thermodynamic significance. His thought experiment showed that acquiring information about a system allows work to be extracted, but only if entropy is paid elsewhere. This was not a philosophical argument. It was a physical one. Recording information creates correlations. Creating correlations constrains phase space. Constraints require energy dissipation. This is why memory formation is irreversible. Consider a camera sensor exposed to light. Photons strike a photosensitive surface. Electrons are displaced. Chemical or electronic states change. A pattern forms. This pattern correlates with the external scene. The scene does not correlate with the camera in return. The direction is fixed. This asymmetry is not perceptual. It is physical. To erase the record, the system must be reset. Resetting requires energy. That energy is dissipated as heat. Entropy increases. This is unavoidable. In biological systems, memory formation follows the same principle. When synaptic strengths change during learning, molecular bonds are modified. Ion gradients are altered. Proteins are synthesized. These processes consume energy and generate heat. The brain does not remember for free. Experiments in neuroscience confirm this. Long-term potentiation, first characterized in the hippocampus in the 1970s, involves measurable biochemical changes. These changes persist. They are stabilized by metabolic expenditure. Memory is not stored as abstract data. It is stored as altered matter. The arrow of time appears because records accumulate. A system that only evolves reversibly cannot remember. Reversible dynamics preserve information but do not generate stable correlations accessible at the macroscopic level. To remember, a system must discard information into inaccessible degrees of freedom. This discarding is entropy production. This principle applies universally. Geological memory exists because sediment layers form irreversibly. Once deposited, layers compact and lithify. The process releases energy. The structure encodes information about earlier conditions. Astronomical memory exists because photons propagate and interact. When a photon emitted billions of years ago is absorbed by a detector, a record is formed. The emission event becomes part of the present state. The reverse process does not occur. The universe is filled with records because entropy has been increasing since its beginning. This leads to a crucial distinction. Information is not the same as memory. Information can exist without records. Memory cannot exist without information being physically embedded. Claude Shannon's information theory, introduced in 1948, defined information as a measure of uncertainty reduction. Shannon's framework is deliberately abstract. It does not specify physical carriers. That abstraction was useful, but incomplete. By the late 20th century, it became clear that information cannot be separated from physics. Rolf Landauer formalized this in 1961 with his principle stating that erasing one bit of information requires a minimum energy cost of kT/ln2, where K is Boltzmann's constant and T is temperature. Landauer's principle does not apply to computation alone. It applies to memory. Every act of remembering is also an act of forgetting alternatives. When a system records a specific outcome, it eliminates other possibilities. That elimination has a thermodynamic cost. This cost enforces directionality. A memory always points to the past because it is created by a process that increases entropy. The record contains correlations with earlier states. It cannot contain correlations with future states, because those states have not yet constrained the system. This is not a semantic limitation. It is a causal one. Future events cannot imprint themselves on present matter without violating thermodynamics. They would require entropy decrease. They would require coordinated microstates arising spontaneously. This does not occur. The asymmetry of memory is therefore identical to the asymmetry of entropy production. This explains why memory is universal. It does not depend on observers. A rock remembers stress through deformation. A metal remembers magnetic fields through domain alignment. A crystal remembers growth conditions through defects. Memory is everywhere because entropy production is everywhere. This perspective dissolves a common misconception. Memory does not cause the arrow of time. The arrow of time causes memory. Records accumulate because entropy increases. Entropy increases because the universe began in a low-entropy state. Memory is downstream of cosmology. This relationship is one way. Importantly, reversible microscopic dynamics are not contradicted. At the level of fundamental interactions, information is conserved. At the level of accessible degrees of freedom, information is discarded into correlations with the environment. The environment becomes a sink for entropy. The system becomes a bearer of records. This is why isolation matters. A perfectly isolated system cannot form durable memories. It can evolve, but it cannot leave records accessible to an external observer. Memory formation requires openness. This principle is exploited experimentally. In quantum systems, isolation preserves coherence. Coupling to an environment induces decoherence. Decoherence produces classical records. It also produces entropy. Thus, memory formation and classicality emerge together. The cost of memory is not optional. It is imposed by physics. Any system that remembers must dissipate energy. Any system that accumulates records must increase entropy. Any arrow of time that is experienced must be physically paid for. At this stage, a deeper connection begins to emerge. Memory is not merely correlated with entropy. Memory is an entropy-producing process. However, this still leaves a gap. Information theory treats information abstractly. Thermodynamics treats entropy physically. The bridge between them must be made explicit. That bridge is the physicality of information itself. The next chapter addresses this directly. It traces the transition from abstract information to physical information and shows why information cannot exist independently of the laws of physics. For much of the 20th century, information was treated as immaterial. It was a symbol, a sequence, a mathematical abstraction. This view was useful, but it was incomplete. Information does not float freely above the physical world. It is always instantiated. It is written into matter, energy, or fields. Without a physical carrier, information does not exist. The realization that information is physical did not arise from philosophy. It arose from engineering constraints and thermodynamic limits. In 1948, Claude Shannon published a mathematical theory of communication. Shannon defined information in terms of probability and uncertainty. His entropy measured the average information content of messages produced by a source. The theory deliberately ignored physical implementation. Bits could be transmitted by electrical signals, radio waves, or any other medium. The abstraction was intentional. Shannon's framework solved communication problems. It did not address energy, heat, or irreversibility. That gap became unavoidable with the rise of computation. Early computers were inefficient, noisy, and unreliable. Engineers treated heat generation as a technical problem. By the late 1950s, it became clear that no amount of engineering refinement could eliminate energy dissipation entirely. There appeared to be a fundamental cost. In 1961, Rolf Landauer, working at IBM, articulated this limit precisely. Landauer demonstrated that information processing has an unavoidable thermodynamic component. His principle states that erasing one bit of information requires a minimum energy dissipation of kTln2, where K is Boltzmann's constant and T is the temperature of the environment. This is not a technological bound. It is a physical one. Landauer's insight was subtle. Not all computation dissipates energy. Logical operations that are reversible can, in principle, be performed without energy cost. What costs energy is erasure. Resetting a bit to a standard state eliminates information about its prior value. That loss must be compensated by an increase in entropy elsewhere. This principle links information directly to thermodynamics. Information is no longer abstract. It has weight in physical law. The importance of Landauer's principle was debated for decades. Experimental confirmation came gradually. In 2012, a team led by Eric Lutz and Antoine Baruit demonstrated the Landauer limit experimentally using a colloidal particle trapped in a potential well. The measured energy dissipation matched the theoretical bound. Information had been measured in joules. This result has far-reaching implications. Every memory reset, every deletion, Every irreversible operation carries an energetic cost. There is no way around it. The arrow of time appears again. If information were abstract, it could be copied, erased, and rearranged freely. If information is physical, it obeys thermodynamics. It cannot be destroyed without consequence. This insight resolves a long-standing paradox in physics. In classical mechanics, information about initial conditions is preserved. In thermodynamics, information appears to be lost. The resolution is that information is not destroyed. It is dispersed into microscopic correlations that are inaccessible to coarse-grained observation. Entropy increase is information dispersal. This perspective reframes the second law. Entropy is not disorder. It is missing information about microscopic degrees of freedom. When heat flows from hot to cold, energy spreads among more degrees of freedom. The information required to reconstruct the initial state becomes unavailable. The system forgets. Forgetting is physical. This connection becomes even clearer in the context of Maxwell's demon. In 1867, James Clerk Maxwell proposed a thought experiment in which a hypothetical demon sorts fast and slow molecules to create a temperature difference without expending work, apparently violating the second law. For decades, this paradox challenged thermodynamics. The resolution came through information theory. In the 1920s and 1930s, Leo Szilard showed that the demon's measurements and memory storage have thermodynamic costs. In the 1980s, Charles Bennett demonstrated that the demon's entropy cost arises specifically during memory erasure. The demon cannot operate cyclically without paying the Landauer cost. The second law survives because information is physical. Quantum mechanics reinforces this conclusion. In quantum theory, information is conserved under unitary evolution. However, not all information is accessible. When systems become entangled, information is distributed across correlations. Local observers experience entropy increase because they cannot access the full quantum state. This is not ignorance. It is limitation. Quantum information theory formalizes these constraints. The no-cloning theorem, proven by Wootis and Zurek in 1982, states that unknown quantum states cannot be copied. This is not a technological limitation. It is a mathematical consequence of quantum mechanics. Information cannot be duplicated arbitrarily. The no-deleting theorem complements this. Quantum information cannot be destroyed without transferring it elsewhere. These theorems enforce conservation at the fundamental level while allowing effective loss locally. Information behaves like a conserved quantity globally and a dissipated quantity locally. This duality underlies the arrow of time. When a system records information, it creates correlations. These correlations reduce uncertainty locally while increasing entropy globally. Recording sharpens one system by blurring another. The universe pays the bill. This trade-off explains why information accumulates about the past. Recording requires an initial entropy gradient. It consumes low-entropy resources. It produces high-entropy waste. Information flows downhill. This also explains why the future cannot be remembered. Remembering the future would require correlations to be established before the events occur. That would require entropy decrease. That would violate thermodynamics. The asymmetry is absolute. The physicality of information also resolves apparent contradictions in cosmology. Black holes, once thought to destroy information, are now understood to obey entropy laws. Jacob Bekenstein showed in 1973 that black holes have entropy proportional to their horizon area. Stephen Hawking demonstrated that black holes radiate thermally. The information paradox arises because information appears inaccessible, not destroyed. Information is hidden, not erased. Across all domains, the pattern is consistent. Information is constrained by physics. Memory formation, computation, and observation are thermodynamic processes. The arrow of time is inseparable from information handling. Time does not flow because clocks tick. Clocks tick because information is processed irreversibly. At this point, a deeper unification becomes visible. Entropy increase, memory formation, and information processing are facets of the same phenomenon. They differ in description, not in mechanism. Yet something remains unresolved. Information is physical, but physics is time-symmetric. How does a time-symmetric substrate generate a directional accumulation of records? The answer requires reframing time itself, not as a parameter, but as a gradient. The next chapter introduces this perspective. It treats time as an information gradient created by the accumulation of records across physical systems. Time does not move. Records accumulate. This distinction resolves a persistent confusion. The arrow of time is not a motion through a temporal medium. It is the direction in which information about the universe increases. Where records accumulate, time appears to advance. Where records do not accumulate, time has no direction. This reframing is not semantic. It is physical. To define time as an information gradient is to say that temporal order emerges from the growth of correlations between systems. Earlier states are those from which records exist. Later states are those in which those records are present. This ordering does not require consciousness. It does not require observers. It requires only physical systems capable of forming stable correlations while exporting entropy to their environment. In classical physics, phase space provides the relevant framework. A complete microscopic description of a system occupies a point in phase space. As the system evolves, this point traces a trajectory. Under time-reversible dynamics, the trajectory can be followed forward or backward. However, macroscopic descriptions do not track points. They track volumes. These volumes correspond to sets of microstates consistent with coarse variables. Over time, these volumes stretch, fold, and filament due to chaotic dynamics. While the total volume is conserved, its fine-grained structure becomes inaccessible. This inaccessibility is information loss at the macroscopic level. The direction in which accessible information decreases defines the arrow. The direction in which inaccessible correlations increase defines the future. In this sense, time is not a parameter but a gradient in informational accessibility. This idea can be formalized. In 1970, Hugh Price emphasized that the arrow of time is not a property of dynamics but of boundary conditions. Later work in statistical mechanics and information theory clarified that boundaries create gradients. Gradients drive processes. Temperature gradients drive heat flow. Chemical potential gradients drive diffusion. Information gradients drive temporal ordering. An information gradient exists when the number of accessible records increases monotonically along one direction. This monotonicity is enforced by the second law of thermodynamics and by the physical cost of recording. Each record correlates a present system with a past state. The correlation is asymmetric. It points backward along the gradient. This asymmetry can be quantified. Consider mutual information, a measure introduced by Shannon to quantify correlations between systems. When a record is formed, the mutual information between the recording system and the source increases. At the same time, entropy is produced in the environment. The net effect is directional. Mutual information accumulates toward earlier states. Environmental entropy accumulates toward later states. The arrow of time is the direction in which environmental entropy increases while mutual information about earlier states accumulates. This relationship explains why memory is reliable in one direction only. Past states constrain present records. Present states do not constrain future records. This is not a causal asymmetry imposed by laws. It is a statistical asymmetry imposed by gradients. The concept becomes clearer in cosmology. The early universe had very few records. There were no fossils, no photons scattered multiple times, no macroscopic structures. As the universe expanded and cooled, interactions occurred. Photons decoupled from matter around 380,000 years after the Big Bang. The cosmic microwave background became a permanent record of early conditions. Every scattering event thereafter created additional records. Starlight carries information about nuclear reactions. Spectral lines encode atomic structure. Gravitational waves encode accelerating masses. The universe filled with information-bearing signals. The density of records increased. This increase defines cosmic time. The future is the direction in which more records will exist. The past is the direction from which fewer records exist. There is no flow. There is accumulation. This framework also clarifies why time dilation and relativistic effects do not eliminate the arrow. In relativity, different observers slice spacetime differently. They disagree on simultaneity. They do not disagree on entropy gradients. The accumulation of records is invariant. Entropy production is a scalar quantity. Information dispersal does not depend on coordinate choice. This invariance explains why all observers agree on the direction of time, even when they disagree on temporal intervals. Quantum mechanics deepens the picture. In quantum systems, information gradients arise through decoherence. When a quantum system interacts with its environment, phase relationships spread into environmental degrees of freedom. The system's reduced density matrix becomes diagonal in a preferred basis. Classical records emerge. Decoherence is not collapse. It is entanglement. The information about relative phases is not destroyed. It is distributed across correlations with the environment. These correlations are practically inaccessible. The system loses information locally. The universe gains correlations globally. This process is irreversible in practice. Reversing decoherence would require manipulating an astronomical number of environmental degrees of freedom with extreme precision. The probability of this occurring spontaneously is negligible. Thus, quantum irreversibility is an information gradient phenomenon. Importantly, the gradient does not require maximal entropy production. It requires monotonicity. Even small entropy increases suffice, provided they accumulate consistently. This explains why biological systems can operate far from equilibrium. Living systems maintain local order by channeling entropy production outward. They build and maintain records, DNA, neural structures, ecological footprints, by exporting entropy to their surroundings. Life rides the gradient. The information gradient also explains why time appears to accelerate psychologically. As organisms age, the density of records increases. Each moment is embedded in a larger archive of past states. Subjective duration is shaped by record density, not by physical time itself. This does not make time psychological. It shows that psychology reflects physics. A universe without an information gradient would have no arrow. Events would occur, but none would be recorded. There would be no accumulation of traces. No history. No memory. Such a universe would be temporally symmetric in every operational sense. Our universe is not such a universe. The gradient originates from the low-entropy beginning. It is sustained by expansion, interaction, and dissipation. It is expressed through thermodynamics, computation, and observation. Time, in this view, is bookkeeping. Each interaction adds entries to the ledger. Each record increases the archive. The present is the boundary between what has been recorded and what has not. This reframing dissolves the illusion of flow. Nothing moves forward. The archive grows. Yet a final problem remains. If time is an information gradient, why do quantum laws appear reversible? Why does symmetry break at all? What mechanism locks in irreversibility when the fundamental equations permit reversal? This question cannot be answered without addressing quantum irreversibility directly. The next chapter examines how decoherence, measurement, and environmental entanglement enforce the arrow in a theory that is otherwise symmetric. At the deepest level known, the laws of physics are reversible. Quantum mechanics does not contain an arrow. This fact appears incompatible with experience. Measurements happen. Outcomes are fixed. Records persist. The past is definite. The future is open. Yet the formal structure of quantum theory allows evolution to proceed equally well forward or backward in time. This tension defines the problem of quantum irreversibility. The Schrödinger equation, introduced in 1926, governs the time evolution of quantum states. It is linear. It is deterministic. It is invariant under time reversal. If a quantum state evolves from an initial condition to a later state, the reverse evolution is mathematically allowed. Nothing in the equation singles out a preferred direction. Nevertheless, every real quantum experiment exhibits irreversibility. A detector clicks. A photographic plate darkens. A pointer moves. Once the outcome is registered, it does not register. The system does not return to a superposition. This is not a failure of quantum theory. It is a consequence of how quantum systems interact with their environments. The key concept is entanglement. When two quantum systems interact, their states generally become entangled. The combined system must be described by a joint wave function. Individual subsystems no longer possess independent states. Information about one system becomes encoded in correlations with the other. Entanglement is reversible in principle. If the combined system is perfectly isolated, the joint state evolves unitarily. No information is lost. Irreversibility emerges when isolation fails. In any realistic setting, a system interacts not with a single environment, but with many degrees of freedom. Air molecules, thermal radiation, vibrational modes, electromagnetic fields. These interactions entangle the system with an effectively infinite environment. The result is decoherence. Decoherence was formalized in the 1970s and 1980s by researchers including lThe and Wojciech Zurek. It describes how quantum superpositions become effectively classical through environmental entanglement. The system's reduced density matrix rapidly loses off-diagonal terms in a preferred basis. Interference effects vanish. Importantly, decoherence does not destroy information. It redistributes it. The phase information that defined quantum coherence spreads into correlations with the environment. Recovering it would require controlling and reversing the state of an astronomical number of particles with extreme precision. This is not forbidden by the equations. It is forbidden by probability. Quantum irreversibility is therefore practical, not fundamental. This distinction mirrors classical statistical mechanics. Classical dynamics is reversible. Entropy increase arises from coarse graining and loss of access. Quantum dynamics is reversible. Decoherence arises from entanglement and loss of access. In both cases, irreversibility emerges from inaccessibility. The arrow of time in quantum mechanics is not introduced by measurement postulates alone. It is introduced by the thermodynamic cost of maintaining coherence. Isolation requires resources. Shielding requires work. Error correction requires energy. In the absence of constant intervention, systems decohere. This is why macroscopic objects appear classical. Their coupling to the environment is overwhelming. Coherence is destroyed on timescales far shorter than any observation. Classical behavior emerges not because quantum laws fail, but because the environment enforces irreversibility. Measurement devices are not special. They are thermodynamic systems. When a measurement occurs, the system becomes entangled with the measuring apparatus. The apparatus becomes entangled with its environment. A record is formed. That record is stabilized by entropy production. The outcome becomes effectively irreversible. The so-called collapse of the wave function is not a dynamical process. It is a bookkeeping update reflecting the loss of access to phase information. This perspective resolves the measurement problem operationally. It does not modify quantum mechanics. It explains why classical outcomes appear. Crucially, decoherence selects a direction. The environment acts as an entropy sink. Information flows outward. Correlations accumulate in inaccessible degrees of freedom. The process is directional because the environment begins in a low-entropy state relative to the system. Once again, the low-entropy beginning of the universe is decisive. If the environment were already maximally entangled, decoherence would not occur. There would be no arrow. The universe's initial condition ensures that environments can absorb information. Quantum irreversibility therefore inherits its direction from cosmology. This connection becomes even clearer in quantum information theory. The no-cloning theorem prevents arbitrary copying of quantum states. Measurement necessarily involves entanglement and decoherence. Information about a quantum state cannot be extracted without disturbance. Disturbance produces entropy. Similarly, the no-deleting theorem prevents arbitrary erasure of quantum information without transfer. Information is conserved globally. Locally, it is displaced. These constraints enforce a one-way accumulation of records. Quantum Darwinism, proposed by Zurich in the early 2000s, extends this framework. It explains how certain states proliferate their information redundantly into the environment. Multiple observers can independently access the same information by sampling environmental fragments. Classical objectivity emerges. This redundancy is not free. It requires extensive entanglement. It requires entropy production. It is directional. The states that become classical are those that are robust under decoherence. They survive because they imprint themselves repeatedly. They dominate the archive. Time, in this sense, selects winners. Quantum irreversibility is therefore not mysterious. It is the quantum expression of the same principle encountered in thermodynamics and information theory. Reversibility holds at the fundamental level. Irreversibility emerges from scale, interaction, and boundary conditions. This understanding has profound implications. It explains why quantum computers are fragile. Maintaining coherence requires continuous error correction. Error correction requires energy. Energy dissipation produces heat. Heat produces entropy. The arrow of time imposes limits. It also explains why the past is fixed. Once records are encoded redundantly into the environment, reversing them would require coordinated manipulation of vast correlations. The probability is negligible. The past becomes effectively immutable. The future is open because it has not yet been recorded. Quantum mechanics does not deny this asymmetry. It explains its origin. At this stage, the structure is nearly complete. Entropy introduces direction. Low-entropy beginnings enable gradients. Memory and information create records. Decoherence enforces classical irreversibility. One element remains. If remembering requires entropy production, then memory has a cost. That cost must be quantified. It must be paid universally. The final step before synthesis is to confront this cost directly. The next chapter examines why remembering the past necessarily increases entropy, and why the accumulation of records is inseparable from thermodynamic expense. Remembering is not passive. It is work. Every record that exists in the universe required energy to form. Every stable correlation that persists across time demanded a thermodynamic payment. Memory is not a byproduct of physical processes. It is an expense item written into the balance sheet of the universe. This cost is not cultural. It is not biological. It is not technological. It is fundamental. To understand why remembering has a cost, one must examine what a record actually is in physical terms. A record is not information alone. It is information that has been stabilized against noise, fluctuation, and decay. Stabilization requires energy dissipation. A transient correlation is not memory. Thermal fluctuations constantly generate fleeting correlations. These vanish. Memory begins only when a correlation is made robust, when it is protected against randomization. Protection requires work. In thermodynamics, work is ordered energy transfer. Work reduces entropy locally by imposing constraints. These constraints must be paid for by increasing entropy elsewhere. The second law enforces the accounting. This is why memory formation is irreversible. Consider the simplest possible memory device, a single bit. The bit has two states. To store information, the system must be driven into one of them reliably. Thermal noise must be overcome. Barriers must be raised. Degrees of freedom must be constrained. This process consumes energy. Landauer's principle quantifies the minimum cost of erasure, not storage. But storage implies future erasure or overwrite. Any finite memory device must eventually reset. That reset has a guaranteed entropy cost. Memory is therefore never free, even in principle. In real systems, the cost is far higher than the theoretical minimum. Biological memory formation involves chemical synthesis, ion pumping, protein modification, and structural reorganization. Each step consumes ATP. Each step releases heat. A human brain consumes approximately 20 watts of power. A significant fraction is dedicated to maintaining synaptic structure and ionic gradients that encode memory. Forgetting is not free either. Degradation processes generate heat and entropy. Memory is an active thermodynamic process. The same applies to artificial systems. Data centers consume vast amounts of energy not primarily to compute, but to maintain and cool memory states. Error correction, redundancy, and stabilization dominate the energy budget. The universe remembers because it pays the price. This price manifests as entropy production. Every durable record requires an increase in entropy somewhere else. The environment absorbs the waste heat. The system retains the correlation. This trade-off is unavoidable. This principle explains a deep asymmetry. It is easy to create new records. It is hard to erase all existing ones. Erasing a record does not restore the universe to a previous state. It generates additional entropy. Even forgetting increases the total entropy. This is why the past accumulates. Records pile up. The archive grows. The cost of remembering also explains why the arrow of time is cumulative. Each generation inherits not only matter and energy, but records. Geological layers stack. Fossils persist. Radiation backgrounds carry imprints of early epochs. The universe does not periodically wipe its memory clean. Doing so would require work on a cosmic scale. The cost also explains why memory density increases over time. Early in the universe, there were few mechanisms for stable record formation. As structure formed, new substrates appeared. Atoms formed. Molecules formed. Solids formed. Life emerged. Each stage introduced new ways to store information. Each stage increased entropy production capacity. The arrow of time accelerates not because time speeds up, but because record formation becomes more efficient. This observation has a precise physical meaning. The rate of entropy production increases as systems become more complex. Complexity does not reduce entropy production. It channels it. Life is not an exception to thermodynamics. It is a thermodynamic strategy. By forming highly ordered structures, living systems create localized memory and control. They do so by dramatically increasing entropy production in their environment. The cost of remembering is paid externally. This externalization is essential. A closed system cannot accumulate memory indefinitely. It would saturate. Entropy would reach a maximum. No further records could form. The universe avoids saturation because it expands. Cosmic expansion provides a continually growing entropy sink. Radiation redshifts. Energy densities dilute. New phase space opens. This allows continued record formation. Expansion is not the cause of the arrow, but it sustains it. This explains why time has not run out. The universe is far from thermodynamic equilibrium. There is still room for entropy to increase. As long as there is room, memory can accumulate. The cost of remembering also clarifies why the future cannot leave traces in the present. Creating a record requires energy expenditure and entropy increase. A future event cannot trigger such expenditure before it occurs. There is no physical mechanism for prepaying entropy. Causality is enforced thermodynamically. This insight dissolves speculative notions of backward causation or future memory. Such phenomena would require entropy decrease. They would require coordinated microscopic states to arise spontaneously. They are not supported by physics. The universe does not remember forward. It remembers backward because backward is the direction of lower entropy. This also explains why predictions are probabilistic. The future is not recorded. It is not constrained by existing correlations. Only statistical inference is possible. The past is constrained by records. It is fixed. Memory makes the past rigid and the future flexible. The cost of remembering therefore underwrites determinism asymmetrically. The equations may be deterministic. The availability of information is not. This asymmetry is what we experience as time. At this stage, all components are in place. The arrow of time arises from entropy gradients rooted in low-entropy beginnings. Memory is a physical process that creates stable records by exporting entropy. Information is physical and obeys thermodynamic limits. Quantum mechanics enforces irreversibility through decoherence and entanglement. Remembering has a cost that cannot be avoided. What remains is synthesis. The final chapter resolves the central paradox. It explains why time does not flow, why it nevertheless has direction, and why the universe behaves as an archive rather than a process moving forward. The paradox is not eliminated. It is resolved. Time does not flow. The universe records. This conclusion appears counterintuitive only because intuition evolved inside the archive rather than outside it. Human experience is shaped by accumulated records, memories, documents, fossils, signals. The sensation of temporal motion arises from immersion in a system whose defining feature is the irreversible growth of information about its own past. The central paradox that opened this investigation can now be resolved. The fundamental laws of physics are time reversible. The universe is not. This is not a contradiction. It is a hierarchy. At the deepest level, physical laws describe how states relate. They do not specify which states occur. They do not encode beginnings. They do not impose direction. They are symmetric because they describe possibilities, not histories. Direction enters through constraint. The universe began in an extraordinarily low-entropy state. This was not demanded by local laws. It was imposed as a boundary condition. That boundary created an entropy gradient. The gradient enabled irreversible processes. Irreversible processes created records. Records accumulated. Time acquired direction. Nothing flows. The archive grows. Entropy increase is not decay. It is bookkeeping. It measures how much information about microscopic detail has become inaccessible. When entropy increases, information is not destroyed. It is displaced into correlations that cannot be reconstructed. This displacement is what stabilizes records. A record is not information alone. It is information protected against erasure. Protection requires work. Work requires energy. Energy dissipation increases entropy. The cost of remembering is written into thermodynamics. This is why memory always points backward. The past is the direction from which constraints originate. The present is the boundary where new records are formed. The future is unconstrained because it is not yet encoded. This ordering is physical, not psychological. Neural memory obeys it. Geological memory obeys it. Astronomical memory obeys it. Quantum measurement obeys it. Every record that exists testifies to entropy production. Quantum mechanics does not evade this structure. It enforces it. At the quantum level, evolution is unitary and reversible. Irreversibility emerges when systems interact with environments that possess unused capacity for correlation. Decoherence distributes phase information into inaccessible degrees of freedom. Classical outcomes appear. Records stabilize. Entropy increases. The environment is not a backdrop. It is an entropy sink. Quantum irreversibility is therefore not fundamental asymmetry. It is inherited asymmetry. It inherits its direction from cosmology. This explains a universal feature of reality. All arrows of time point the same way. Chemical reactions, biological evolution, geological layering, stellar life cycles, and human history align because they share a common low-entropy origin. The arrow is global because the boundary condition is global. There is no local arrow generator. This also explains why time does not reverse locally. A region of space cannot spontaneously generate an opposite arrow because it would require local entropy decrease against the global gradient. That decrease would need coordinated microscopic states that do not arise naturally. The arrow is enforced statistically, not dynamically. This distinction matters. It means that time's direction is not a force. It is not a field. It is not a flow. It is an emergent ordering imposed by information constraints. Time is not something that happens to the universe. Time is what the universe remembers. This reframing resolves several persistent confusions. First, it explains why the equations of physics work equally well forward and backward while experience does not. The equations describe reversible possibilities. Experience is shaped by irreversible record formation. Second, it explains why entropy increase does not contradict structure formation. Structures are records. They exist because entropy is exported elsewhere. The more structure the universe builds, the more entropy it produces. Third, it explains why the future cannot affect the present. The future does not yet exist as a record. There are no correlations to transmit. Causality is enforced by thermodynamics. Fourth, it explains why prediction is probabilistic and retrodiction is constrained. The future lacks records. The past is saturated with them. This framework also clarifies the ultimate fate of the arrow. As the universe evolves, entropy continues to increase. Stars burn out. Energy gradients flatten. Black holes dominate. Eventually, the universe approaches thermodynamic equilibrium. At equilibrium, record formation ceases. This does not mean time stops. It means the archive stops growing. A universe at maximum entropy would still possess spacetime structure. Events could still be labeled by coordinates. But no new records would form. No durable correlations would arise. History would end not with destruction, but with silence. The arrow would disappear because there would be no gradient left to sustain it. This outcome underscores a final insight. Time exists only where there is room to remember. The low-entropy beginning created that room. Expansion preserved it. Entropy production fills it. When it is full, time, as an ordering of records, loses meaning. This conclusion does not diminish time. It grounds it. Time is not an illusion. The illusion is motion. Nothing in the universe moves from past to future. Instead, the present becomes increasingly constrained by accumulated records. The past is fixed because it is encoded. The future is open because it is not. The universe does not travel forward. It writes backward. This writing is relentless. Every interaction leaves a trace somewhere. Every trace consumes free energy. Every consumption increases entropy. The ledger never resets. The arrow of time is therefore not an arrow at all. It is a gradient etched into the structure of reality by its beginning and enforced by thermodynamics. The paradox dissolves. Time does not flow, it archives. Goodbye. Or perhaps. See you in the next frame of understanding.